Good morning, everybody. Welcome back. We are at least I am about 1 week into my home quarantine in the middle of the COVID-19 pandemic crisis. And it's a little crazy around here. I'm in a house. I have 6 kids, my wife and I, and several pets. And I feel like I'm living in the middle of a zoo right now. So if you hear weeping and wailing and gnashing of teeth, screaming, pounding on the door, just ignore it. Those are my kids wanting my attention while I record this lesson, which I will go give to them as soon as I'm finished. But for the time being, I'm giving my attention to you because I am very excited to introduce to you a topic that you're not going to hear in too many places, at least at the undergraduate and even graduate level of education, which is a little surprising to me because this is a really important topic, in my opinion. I was introduced to it, interestingly, as an engineering consultant in industry. And a couple of my colleagues who were fortunate enough to be introduced to it in graduate school introduced it to me on some projects, and I thought, where have you been all of my life? This concept of critical state soil mechanics. And so I felt like it would be important to introduce you to this topic. And for the final 3 lessons in this class, I'm going to focus on critical state soil mechanics. So a lot of these slides are going to have a lot of text. So feel free to pause my speaking if you'd like, if you want to read through. There's a lot of good material that I've summarized and written here. And I did that because a lot of this stuff is difficult to show graphically without an explanation to go with it. So excuse my text on a lot of these slides, but it was honestly the most efficient way that I could get the information you need to know to you. So let's just summarize, right? Up to this point in your education as a geotechnical engineer, you've likely treated things like settlement and shear strength evaluation as completely separate things. The idea of consolidation, behavior, shear failure of a soil, 2 totally different phenomena, right? But the truth is that they're related phenomena and they come from the same fundamental mechanics. And so if we connect these phenomena, we can and develop a framework that can describe both simultaneously, then we can predict the engineering behavior of soils using that one single framework. So this framework that I want to introduce to you is become known as critical state soil mechanics. Now you'll recall critical state, that sounds like something from like a Mission Impossible movie or something, right? Mission Impossible, what are we at now? Mission Impossible 14, Mission Impossible 15, a critical state. Well, anyway, that was my lame attempt at jokes. That was a dad joke, I'm sorry. So the idea with critical state is if I have, for instance, strain on one axis and I have stress on the other axis, and I load up, say, a very dense, high relative density soil, it'll show strain hardening behavior, and then at large strains, it's actually, I'm sorry, strain softening behavior. And it's strain softening behavior because as the soil is strained, it loses its peak strength and will eventually converge to some residual shear strength. If I were to load up in triaxial loading a very loose specimen of the same soil, it might show something that looks like this. So that would be like strain hardening behavior. But you'll notice that whether the soil was had a high relative density or a low relative density to begin with, at high strains, they all go to the same place. And so what that means is the fabric of the soil becomes so disturbed that the initial relative density or the initial state of that fabric, does not matter. And so this is why we call this the critical state, meaning it's the state of the soil where its fabric is universal, and it corresponds generally to a residual. Often we'll call that the residual strength of the soil, right? So when we talk about critical state soil mechanics, what we're talking about is a framework of analysis that's designed to handle and accommodate the soil based on the properties of that soil in that critical state. So when we talk about friction angle, we're not talking about the peak friction angle or the softened friction angle. We're talking about the friction angle of the soil at that residual state. Thus, it doesn't matter if the soil was had a high relative density or a low relative density. The critical state friction angle is the same for that particular type of soil, regardless of its initial relative density. And this critical state soil mechanics is then going to tie together the concepts of one-dimensional consolidation and shear stress versus normal stress behavior. So you're going to see a lot of plots that will look like this in these next 3 lectures, and I want you to become familiar with them. So you'll see a plot that will look something like this, where we'll either have tau or maybe q prime, depending on whether we're in more Coulomb 2-dimensional space or stress path PQ space. So you'll see plots that'll look like that. And then directly below that plot, you'll see plots where the x-axis lines up with the plot above in terms of confining stress. And then you'll see void ratio plotted on the y-axis. And then maybe to the right of that, you'll see another plot that looks something like this, where you'll again have void ratio, but maybe you'll have the ln of P or the ln of sigma prime. So the idea is that you'll go from this plot to this plot, and then from this plot to this plot, and everything projects onto the different planes. So get used to that idea, because we're going to see a lot of it in the next couple of slides. So these next series of lectures, these next 3, this is the first of 3, they're going to focus on a very basic and a very simplistic critical state soil model, CSSM model. I don't like CSSM. I always forget that S, so I just call it CSM, critical state model. So I use those terms interchangeably. If you see CSM or CSSM, it means the same thing. It's a critical state model. This research really became hot in the 1970s, 1980s, 1990s, and it even continues today, though less frequently, because a lot of the fundamental theories have already been established. The basic model I'll be introducing to you is a useful model, and you can use it in practice. There's a lot more sophisticated and more accurate models that are out there now. They're also more complicated, but if you can wrap your arms around the basic model that I'll introduce to you in these 3 lessons, you'll be much better prepared to learn on your own more sophisticated critical state models. So buckle your seatbelt. This is going to be a really exciting series of lessons for you, I hope. I would estimate that probably less than 15% of practicing geotechnical engineers even understand the basic concepts of critical state soil mechanics. So even by learning these lessons, you're really setting yourself up to be unique among your colleagues and to be able to have some skills that hopefully will be useful to you in your career. So for references, I just want to point out that all the material coming on these next 3 lessons is being pulled from essentially 2 sources of mine. So one comes from a presentation that a good friend of mine, and he's a geotechnical legend in his own right, Professor Paul Main from Georgia Tech University, he gave in 2006, and he gave me a PDF copy of his lecture. And so a lot of the material I'll present is pulled from that lecture entitled Critical State Soil Mechanics for Dummies, which I liked because when it comes to learning that new topic, sometimes I felt like a dummy. But he made it very understandable and put things into terms that made sense to me. So I have included a PDF copy of this down in the notes for this video. There'll be a link to download it from my Dropbox folder. The second source for this lesson comes from the textbook that we're using. The textbook, I have it right here. It's from Muni Budhu, the Soil Mechanics and Foundations textbook for your class. So this will be in Chapter 8 if you have the second edition, or it will be in Chapter 11 if you have the third edition. And I've listed several more references here that you might find useful if you want to dive deeper into this concept and idea of critical state soil mechanics. So, before we jump into the weeds, let's discuss a little bit of why we do critical state soil mechanics. So, even a very simplistic and basic critical state model can help us predict many of the complex soil mechanics behaviors that we've discussed this year. Those behaviors include, but are not limited to, by the way, normally consolidated and over-consolidated shear and consolidation behavior, undrained versus drained stress paths in shear loading, positive and negative pore water pressure development during shear, volume change during shear, either contraction or dilation, undrained shear strength prediction, and soil constitutive behavior. So this is predicting stress-strain behavior. If I stress the soil, how much is it going to strain? Or if I want to strain the soil this much, how much stress would do that? So the basic requirements that you will need to use this simplistic critical state model are simply these terms. And these terms should all be familiar to you. We have the friction angle, but remember, this isn't the peak or the softened friction angle. That's the critical state friction angle. So you'll see it like this, C sub S, meaning the critical state friction angle. You have C sub C, which is the slope of the virgin compression line. It's often called the compression index of the soil. You have C sub R, also from the consolidation curve. That's the recompression index. That's the slope of the consolidation curve on the rebound portion of the curve in void ratio and a log of stress space. We have the void ratio of the soil. We have the effective vertical stress of the soil and the soil's over-consolidation ratio. So that implies that you need to know the pre-consolidation stress. Or I guess another way to write that is sigma prime P. So these are the terms you need to be able to build and use this basic critical state model. And all of these terms should be familiar to you. You should know how to obtain all of these terms through laboratory and even laboratory testing and field tests or approximations. So, despite the fact that this is a powerful and simple framework that can be very useful to geotechnical engineers, most geotechnical textbooks do not include it or don't talk about it. And most of the curricula in the United States, at least, for undergraduate and graduate geotechnical education also does not talk about this. Fortunately, our colleagues on the other side of the pond, over in, say, the UK and other parts of Europe, they're much more passionate about critical state soil mechanics. And in fact, many of the discoveries, the most significant discoveries from critical state soil mechanics happened in Europe, in the UK. And so a lot of the text and resources that we have comes from our colleagues in the UK and Europe, and we're certainly grateful for that. And I hope that critical state soil mechanics will become more adopted and accepted here in the United States with time. So here's a couple of the premises of critical state soil mechanics. So think of these as the underlying assumptions of our critical state framework. Assumption number one, or premise number one, the soil does not fail under consolidation loading. In other words, if the soil is consolidating, it can handle infinite amounts of loads and it will not fail. It will just consolidate further. But shear loading is what fails the soil. Okay, so that's premise number one. Premise number two, all stress paths or loading paths are going to approach something called the critical state line. Premise number three is that failure occurs when the stress or the loading path reaches the critical state line. So you can think of the critical state line as, in essence, another representation of a failure envelope. Premise number four, unlike the Moore-Coulomb failure criteria, or the failure envelope we discussed, that is has a friction angle or a slope equal to the friction angle and a y-intercept equal to the cohesion, the critical state model incorporates volume change into its framework. So the Moore-Coulomb failure criteria completely ignores the idea of volume change, but critical state doesn't, because it's inherent and important in the critical state framework. Premise number five, because critical state models deal in the realm of volumes, we deal in 3 dimensions. So it's going to incorporate invariants. And you remember, invariants are things like the mean stress. And so P prime and Q are what we're going to be dealing with. So everything is going to be handled in PQ space, stress path space. And premise number 6, the critical state soil mechanics is most effective when soil is treated as a continua. Almost think of it like an infinitely extending mass, or like a mesh, right? Something that you would see in maybe like a numerical model. So if we treat it as a continua with smooth changes of stresses and strains, the critical state model works great. It's not effective when we start to introduce real life things like shear bands or non-uniform strain distributions. So an example of that might be from a direct shear test, where we have corners of the shear box where the soil is not allowed to strain. So the direct shear test, for instance, would not be a good test to represent or to develop a critical state model from. Okay, so those are the premises. Let's move on. And let's introduce you to some of the basic parameters of this simple critical state model. So, as I warned you, we have our 3 plots. On the upper plot, we have the PQ space, so stress path space, and you can see the failure envelope here labeled as the critical state line, and it's going to have a slope. And we're going to call this slope M sub C for compression and ME for extension. So that's our modified failure envelope. And if we're above the p-axis, so if we're in this range right in here, the soil is being sheared in compression. And if we're in this range down here, the soil is being sheared in extension. And note, by the way, that the slope of the failure envelope in compression is steeper than the slope of the failure envelope in extension. That's one of the nice things that the critical state framework allows us to consider. So, for axisymmetric compression, meaning that if we have a three-dimensional soil element, all of the axes are being compressed simultaneously at the same time, that slope is going to be equal to this term right here. It's a function of the critical state friction angle. For axisymmetric extension, then the slope of that modified failure envelope in the extension space is going to be equal to this equation right here. Notice the only difference is the plus or minus sign in the denominator. Okay, from stress path space, we can move down here and project onto void ratio versus mean stress space. And if we look down here and we project that critical state line onto that space, it becomes a curved line. The critical state line is curved. And interestingly, if we were to plot the consolidation curve onto this space, it would look like this. Notice how it's parallel to the critical state line, meaning that, again, remember, failure occurs when we reach the critical state line. Therefore, if we're consolidating the soil and it's normally consolidated, it will never reach the critical state line because it runs parallel to it. But if we rebound the soil and over-consolidate it, then the rebound line does something like this. And then it's possible to cross the critical state line. But if we reload it, it will come back and we'll be back on the normal compression line. So NCL is the normal consolidation line. It's equivalent to a consolidation curve. And the URL is the unload or reload line of the consolidation curve. Okay, so now if we project from this view over to this view, or now we have void ratio versus mean stress, but this time mean stress is on a log scale, our curves straighten out into lines. Now the slopes of these lines we can calculate. The slope of the normally consolidated line, the normal consolidation line, is the same as the slope of the critical state line, and we'll call it lambda. And we can calculate that using this equation right here, where it's just C sub C, but instead of being in the log base 10 units, we're in natural log units. So we have to convert that C sub C to an equivalent in natural log. That's why we divide by the ln of 10. And for the unload or rebound line, we're going to call that slope kappa. And it's going to be the C sub r from our consolidation curve, but just corrected to natural log units instead of log base 10 units. So hopefully that introduces you to various parameters we're going to use. So let's move forward. Because the critical state model works with three-dimensional stresses and invariance P and Q, all of the vertical stresses need to be converted to three-dimensional mean stresses. So we're not dealing anymore, folks, with just vertical stress. We're dealing with mean stresses. So we have to calculate mean stresses from our vertical stresses. So here's how we're going to do that. First, let's look at our pre-consolidation stress. Now, if we assume that our at-rest earth pressure coefficient, remember the at-rest earth pressure coefficient gives us a horizontal stress. It's going to be the earth pressure coefficient times the vertical stress. If the soil is at rest and everything is in equilibrium and nothing is moving relative to other things, then we're going to say it's the at-rest earth pressure coefficient. And geotechnical engineers commonly use this equation right here to get that at-rest earth pressure coefficient. So if we assume then this equation for our at-rest earth pressure coefficient, and we want to get the mean stress associated with the pre-consolidation stress, so we'll call it the pre-consolidation mean stress, it's going to be equal to this relationship right here, where sigma prime c is our pre-consolidation stress, just the vertical component of that. And then you can see we have our critical state friction angles. So that's the first step. We convert our vertical pre-consolidation stress to a mean pre-consolidation stress. And then similarly, we have to convert the initial vertical effective stress. That's got to be converted to its corresponding mean stress. And we're going to do it using this relationship right here. Now remember, the over-consolidation ratio is simply the ratio of the pre-consolidation stress to the current effective vertical stress of the soil. Well, awesome. So now we have a pre-consolidation mean stress and a vertical mean stress. And with those, we can come up with an equivalent over-consolidation ratio for 3 dimensions. And we're going to call that invariant R. So it's not OCR anymore, we're just going to call it R. And it's simply the ratio of the pre-consolidation mean stress divided by the vertical mean stress. And sometimes people call it R star, same thing, okay? And it's going to approximately be equal to this relationship right here. So all it is the ratio of these 2 equations. Okay. So now you are prepared to be introduced to the concept of a yield surface. So one of the integral components or parts of the critical state model is the idea of a yield surface. So understand some basic components of a yield surface. Let's go here to this plot, and I'm going to plot things in terms of P and Q. Whoops, I got that backwards. P and Q space, and I have my modified failure envelope that has a slope of m sub c. Now, these failure surfaces are essentially circles, ellipses, bullets. They're different shapes. And they always correspond to whatever the pre-consolidation mean stress is of the soil. And as long as my stress path of the soil remains inside of this sphere, it doesn't matter which direction it's going, as long as that effective stress path remains inside of that sphere, the soil is going to behave elastically according to the rules of this critical state model. Now, here's the rule though. If the effective stress path ever reaches the yield surface, the effective stress path can never go outside of the yield surface. So even if it travels and it wants to move outside, the yield surface will expand and will essentially grow to accommodate that stress path going outside of its boundaries, okay? So it's going to look something like that as this stress path continues to move outside of the yield surface. And once a yield surface is expanded, it generally can't go back. The one exception to this is if there's a stress path that crosses the yield or the modified failure envelope up here. So if it crosses the modified failure envelope, you'll notice that there's this component of the modified failure envelope inside the yield surface. The soil will not fail if it reaches that failure envelope. It can only fail after it first reaches the yield surface, and then next reaches the critical state line. That's when a soil will fail. So if the stress path reaches the critical state line before it's reached the yield surface, it's not going to fail. But if it does reach the yield surface, this is a unique rule that is triggered. Instead of expanding, what happens is the yield surface contracts. So that circle will, in this case, begin to shrink. Okay? And this effective stress path is sucked back in with the yield surface and brought back eventually to the critical state line and to failure. So those are kind of the basic rules, and we'll get to that in a minute, but I wanted to just introduce that concept to you. So back to this plot of this yield surface. So this yield surface is going to separate the states that correspond to elastic behavior, which is everything inside of the yield surface, to plastic behavior, which is what happens once you reach the yield surface. You start to have plastic behavior. So in the basic critical state model that I'm teaching you, we're going to use an elliptical yield surface. And here's the equation for the yield surface. So M, if I'm in compression zone, that's going to be M sub C. If I'm in the extension zone, it's going to be M sub E. And it's going to be equal to this equation right here. And that will give me the equation for the surface that I'm dealing with. Now, one of the rules is, note that the critical state line always passes through the very top center of the surface, okay? And that's one of the rules. So the yield surface will always peak right on the critical state line, whether it's a circle, an ellipse, or whatever. So this model that we're going to be dealing with is essentially an elliptical surface. Other researchers have proposed other surfaces like bullets, circles, triangles, cones, all sorts of different shapes. But we're just going to deal with an ellipse in these lectures. So as long as that effective stress path, ESP, so that stands for effective stress path, stays inside of the yield surface, the soil will behave elastically, okay? Once the effective stress path reaches the yield surface, the soil will begin to yield and will accumulate permanent deformations, and then if it's drained, volume change will occur. If it's undrained, volume change will not occur, but the stress path will begin migrating immediately to the critical state line. So once the effective stress path moves beyond the yield surface, the surface expands with that effective stress path. So the rule is the effective stress path must always be within or on the yield surface. It can never be outside of the yield surface. Okay. That's the end of the introduction to critical state soil mechanics I wanted to give. In the next lesson, we're going to talk about how we can predict the stress paths, the different loading stress paths using this critical state model. But this lesson today was just intended to give you the basic terminology and understand some of the basics of the critical state framework, including the critical state line, the idea of yield surfaces, the idea of using invariants to represent our stresses. And so chew on those concepts, and then you'll be prepared for part 2 when we deal with predicting stress paths with the critical state model. Look forward to it. Thanks for your attention, everybody, and I'll see you next lesson.